session, basically last lecture session of the Gyan. So in this session we will discuss about things, how to extract, how to get those values as per device perspective. Okay. So we will discuss it. This will be coming out for our discussion. You will ask as many questions as you can, and we will try to answer those questions as much as possible. So basically, when I was saying we are discussing yesterday about this, then I was showing you this structure. So this kind of structure is something known as TLM structure. TLM structure. Some people say transfer length measurement, some people say transfer line measurement. Actual name each according to this transfer length. Okay. What is this TLM structure? So let's come to again to the problem statement. What do you want to do? Yesterday we learned that we have created the devices. Right? We have fabricated the devices, we got the material, we fabricated the devices, now we characterize it. So usually device level characterization, there are a lot of material characterization which Ariel talked about, L10, Raman, things which will give you the different material characteristics. But once you make the device, then we need some device characteristics which you can do using the material characterization. One of the famous things that for the 2D material, we discussed about serious problem with contact resistance, right? And I discussed yesterday what is contact resistance. It's resistance at the interface. But question is, how do you find that? Because if you are reducing the contact resistance of a system, until unless you don't extract that, then it will be difficult how to, whether actually you are getting reducing the contact resistance, getting reduced or not. And there is no direct method which can give you directly the contact resistance. We have method to measure the resistance. You can apply voltage, you will get certain current, but that will give you total resistance, right? But we have to find out somewhere, we have to find out contact resistance. So let's discuss the method how to find out that. So whatever you discussing are all practical scenario, practical things. Theoretical, there are method of finding the contact resistance. Practical activity. So you have device, right? You have a 2D material device. You have substrate. On substrate you have place some 2D material, and then you have two contacts. That we learned yesterday, right? So now you have two contacts here. So what we will do, you can apply voltage in the first session. You learn that you have SMU. From that you can apply voltage and you can get the current. So only which you can put certain voltage, which you can put by probing, which we will learn in the next session, that how to do the probing in the lab. We have probe tip, we can do the probing with the pad, different pads, and we can give the voltage and it will give you the current. If it will give you the current, this current R you can find out D by I. This you can find out noise, right? But this R is a total R. It will be R of your this resistance, contact resistance. This will be R of this contact resistance, and this will be R of this channel also, because we have find out total voltage between two pads, these 2 points. So V by I and the path the current is this. So if you do V by I, this will give you total resistance, right? And this total resistance R will be basically 2 into RC. There are 2 interfaces there, right? Per time we imagine, assume that both interfaces are ideal. And usually in practical case this is not ideal. But let's assume that both interfaces are almost ideal. 2 contact resistance, plus we have channel resistance. This will be your total R, right? Total R you can find out total, right? Now, we have to find out our goal is this. Right? This R we can calculate by V by I, which we know. So this R is known. RM I am telling you R measured, right? And this is R channel CH. Okay. Understood this? Now beauty is we have known formula or we know about this R. This R is basically your resistivity into length divided by area. No, right? So what will be total measured R will be 2 into RC plus resistivity into length divided by area. Where length is the length between 2 points you have probe. This length between 2 points where you are forcing the applying the voltage. So what is the practical thing what usually we can do here? Basically, what we'll do here will take instead of area, it will become your length because atomic. So whatever rho you are given area, so this will be your 2 into RC plus rho into L by area will take whatever process area. This will give you width into height, right? What you can do is width into height, right? 2D material has a width. Height it has just atomistic scale. So what you can do, whatever R you will row, this will be combine your height also. What you can write here, I would have discussed this in the next step. You ask me. So what you can do, total Rm will be 2 into RC plus rho prime I am saying into L by W. Where you rho prime and rho prime is basically resistivity per unit height, which is known as seat resistivity. Right? So for 2D material, which is known as seat resistivity, then you use seat resistivity. Okay. Basically your resistivity per unit height. Okay. Now things are clear? Understood? So now, so what basically your knowledge, we are creating this type of a structure. See here now, how to find out the contact resistance. We are creating this type of a structure, and in the structure we are putting multiple pads, multiple fingers with a variable distance. This is this paper 1 micrometer, 2 micrometer, 3 micrometer, 4 micrometer, 5 micrometer like that. So we have multiple pads with multiple distance. So we have certain table, then we can prepare a table, right? For each measurement, we have RM, right? Each measurement we can find out RM. So RM we have for each measurement. And with length, let's say, this is R1, length L1, R2, L2, R3, L3. So we have RM when length was 1 millimeter. We have R2, RM when length was 2 millimeter. We have something like that. So if you take this equation, where if you take RM and L as independent variable here, if you plot it, it's your standard y equal to mx plus c, linear equation, right? So this plot will come like something this. So slope will be rho prime by w, and interface will be something like 2RC. Right? If you plot this equation, here your RM and here your L. Is it fine for you working? If you plot this equation, take on x-axis you take L, y-axis you take RM, and plot it. Then this interface will give you 2 into RC, and this slope will give you rho prime by W. Is it fine? So it's a standard equation. So what we can do, by varying this length, we can prepare that table, and then we can plot that table so that we can plot that table, right? So if you plot that table, first thing that this should come linear almost. It will not come perfectly linear because ultimately there are a lot of issues there. So if you plot this, then it will come from that point here, 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 here. Something like point will come. So you can take average value and you can plot something like this. So this will be correspond to this equation. So in the single measurement, it will give you one. In this interface will give you contact resistance of, and your this slope will give you seat resistivity also because W you already know. Width of the this is your channel width that you know. So in single measurement, you can find out contact resistance also, and you can find out your materials resistivity also. This is a very powerful method in the electrical comparison, which is L10 TLM method. Understood? So this is a very powerful measurement whenever you create device. Now the troubleshoot what we have to do first thing. We have assumed this I will be over to L by A, where W should be constant, right? Means that if you make your device, it has to be very rectangular. I was discussing yesterday that in some applications you have to make it rectangular. Here we assume W is constant, right? So you have to make it rectangular. So to make it rectangular, what you have to do? If you do the exfoliation, you have to etch it before that. Etch so that make it rectangular, and then you can make this TLM structure. This will give resistivity and then the contact resistance. Why this deviation is? Ideally, it should not deviate. Ideally, you all should follow the same line. But why its deviation is basically, we have assumed that this is also constant. Resistivity is a material's internal property, but 2D material has a lot of defects. Whatever material you get, you will not get single crystal. Somewhere you can find more defects, somewhere you can find less defects. So in fact, even resistivity is not very constant. So due to that, you will get this kind of deviation.
So rectangular has the advantage
If you note that this is the linear equation only when your W is constant, right? Anything is fine. You can take a square, it's fine. Only thing is width should not. Anyway, 2D material square will be very difficult because this you have to go for in the range of micrometer. You cannot place two contact in the nanometer. You have to be very difficult. You have to put micrometer. So at least you need 10 micrometer plate length. So getting 10 micrometer length and 10 micrometer width is very difficult. That's why I'm telling you to it will be rectangle. Okay. Do the exfoliation. Width will be smaller and length will be larger. If you want, then you can take a square root protocol. Only thing is pretty fat. Understood? So this is a very powerful method. And now the contact resistance as well as seat resistance. Okay. Clear? Only thing is that process you have to create multiple pads. You need longer, larger plate size so that at least don't have data point you should have. Then you can find out. So these are fingers. So later it will get connected to the middle pad.
So apart from mapping, none of your conflict is touching the substrate also.
So that some of the contacts
It's touching the substrate also.
but substrate is insulator. Current flow path you know that. I'm looking at only going to current flow path.
So since it is insulator, there won't be
So that's insulator. Very good question. So that is insulator. So current will not flow through that path. Okay. So for this, you have to find out you have to fabricate the TLM structure. But this is the most famous method of contact resistance and the seat resistivity extraction of thin film. If you don't know for the contact material, all kind of thin film. This is the very most powerful method and very famous among the device setters community. Okay? problem is that to find out here the main disadvantage you have to make the multiple fingers, right? Sometimes you will get bigger flake, longer flake at early stage. Sometimes you don't have a fine features. I have many other limitations also. So in any other methods, there are one more processing method. Yes, of course, there will be many more. One more change. So this is RC or C we have extracted in the TLM method. Which is known as Kelvin probe method. What is the Kelvin probe method? I think most PCs know about this. So SMU to measure, SMU has very nice feature that if you have any type or any SMU, if you probe it, you can probe that in high impedance mode also. Means the stick can give you the voltage difference, but it will not allow any current for that. This is the forcing condition with high impedance mode you can probe. So what we can do, we can create a structure something like this. We have a device. Let's say this we have two different device. So what we'll do, we'll put fingers here, two pads here, and here. Like we have put it here. One pad we have put here. This one, another pad we have put here. This one. So these two pads we have put here. And through this two pads, we force a certain current or certain voltage, will force it. Will supply certain voltage so that current should flow through this line. Okay, it will flow. And then what we'll do, just adjacent to the contact, not use touch, adjacent to contact, we'll create one more pad here and here. And on these two pads, I'll just measure only voltage in high impedance mode. If current should not allow from this line, I'll only measure the voltage in the high impedance mode. Right? So let's say if you are giving V2 here, or V1 here, and V2 here, and total I you can find out V2 here, whatever, V2 minus V1 divided by total resistance. Total I you can find out. Total I is known here. Because forcing to instrument, so instrument can give you reading how much I you have forced. Right? And this I is known, right? This voltage is known. And this voltage I can measure in high impedance mode. So resistance of this area, which will be your contact resistance, that will be yours. This V1 minus this V1 prime divided by R. Right? You are getting or not? This will be your resistance of this contact area. Here, I am forcing about this. From here, I know the voltage and I am sensing here. So this contact and this contact are same. So V2 I have sensed here, V1 I have sensed here, which is just nearby this. So if I give V1 minus V2 divided by I, this will give me the resistance of this local area. Understood or not? Where is the path?
So in this picture, where we have the contact resistance.
This is one contact and this is one another contact. Two contact I have put it. What is current from path? I am forcing current is going from here to here. So current is entering from metal to the graphene, going inside channel and again going from graphene to metal. This is the current flow. Current is not coming in this direction or this direction because this I have forced to the high impedance. I am not allowing any current to this way. You can go using a SMU, high impedance. So I have forced. So current flow path is this way. So if I can know the voltage of this two path in, means this probing voltage I already know V1. If somehow I know the voltage just after the interface, if this is the interface, this area interface is just immediately after the interface, I can found out voltage of this point. Then by reducing V1 will be known, this voltage is known, and how much I is flowing is known. This V1 minus V2 by I will give me resistance of this interface only. Agree you? Now, this will give resistance of this interface only. So you can directly find out resistance of this interface. And similarly, you can directly find out resistance of this interface also. So all kind of interface you can find out resistance. This will give you one shot, this will give you the resistance of that particular interface. Right? And we have calculated like this, using this method, we have calculated using the method, and both are matched. Only thing you have to be very precise that trying to leak through this path, trying to leak through this path with this method, So this is another method, but creating this kind of device will be very, very complicated rather than creating the TLM structure. And if I suggest all of you, if you have to find out the contact resistance, then go to the TLM structure. If you have some limitation in creating the TLM structure or lot of problem, then you can choose this approach. But generally, TLM is the most promising method till now to find out the contact resistance of any input. Understood?
Yes, sir.
Another question, some ask me. Now another thing is any kind of material characterization if you get, then take any physical equation and then from physical equation you try to correlate the parameter which you can measure. And then from measurable parameter to the whatever parameter you are finding, you can try out to find a value using certain plot or something. That will help you a lot. For example, let's say another example is a standard IV characteristics. Yesterday I discussed like mu, COX, W by L, VGR minus VT, all is correct. So if you make any device or transistor, you have to find out so many things. Threshold voltage. Threshold voltage you have to find out. So usually threshold voltage you can find out. You know all the what is threshold voltage. Here what I did, I have plotted IV, I versus VD. But similarly you can tune the gate voltage also, right? And then you can find out ID versus VG. ID versus VGF, VGS, fine. And this if you find out, it will give you characteristic something like this.
Okay. Yes, sir, I am filling my presentation. Okay.
Not
1 minute, sir. 1 minute, sir.
Like previous session, we have one more industry session, and this will be by Tushar Salgire. And
Yes, sir.
yeah, Mr. Tushar Salgire, and we will discuss about different aspects of the power stations and how we can utilize the power station in the electric crisis. Mr. Tushar, what do you please continue?
Okay, sir. So my name is Tushar Salvi from my instrument. Hello. Hello.
Yeah, please continue.
Okay. My name is Tushar Salvi from my instrument. Introduction, 8 professional sequence. Perfect. Okay. So, sir, 1 minute, sir. Okay, sir, hello. Hello.
Yeah, please continue.
Okay, sir. Hello. Hello.
Yeah, Mr. Tushar, please continue. Yeah.
Okay. तो सर मैं कंपनी की शुरुआत 2011 में हुई थी। तब से हमारा लगातार ग्रोथ और इनोवेशन को फोकस कर रहा है। तो शुरू से ही हमारा एम था कि इंडिया में स्पेसिफिक और इंजीनियरिंग एजुकेशन को सपोर्ट करें।
Mr. Tushar, please try to mix some English word also as much as you can. I'm not saying that speaking complete English, but because we have audience here from the white background, so please mix in English and as much as possible. Okay.
Okay, sir. Okay. So yes, sir.
Yeah. Please continue.
Okay, sir. So your company was established in 2011 with a clear vision to design and manufacture high quality scientific and engineering instruments that support learning, research, and industry across India. We are headquartered in Indore, Madhya Pradesh, which serves as a strong base for serving clients and institutions all over the country. The company is registered under MSME and Startup India, reflecting the recognition as a government approach and innovation in enterprise. Over the years, we have successfully delivered projects to some of India's top institutes and government bodies. Earnings their trust is our commitment to quality design and reliability. And let's start my presentation. Okay. So my instrument has been we are manufacture variety of scientific and engineering instruments for education area, let's set up and research area of materials that you have user specific customization for industry and research. Okay. So material science is from fundamental to functionality. How material science transforms ideas into real world and empirical finance, processes, and research. This is material science. Major projects is material science, finance, processes, and research. Okay. Finance is a fourth type. Treatment instruments used to change physical property of sample at very high temperature. For example, 100 degrees Celsius, 200 degrees Celsius, 300 degrees Celsius, and 600 degrees Celsius to 1000 degrees Celsius. These laboratory finance are widely used in scientific experiments in physics labs, steel and paint industries, biotech companies, and small industries product etc. Their major applications include general laboratory testing, material testing for analysis. Finance features are fully controllable provision for external sensors, data protection facility. These are interfacing to RF switching to USB interfacing facility. And next project transfer. The material science major project transfer from 2011 to 2013. 2013 to 2013 and 2013 to 2014 the project transfer from 2011 to 2014 the environment called state unit state. Okay. So semiconductor wafer. So semiconductor wafer is a silicon material in gallium nitride, silicon carbide. Semiconductor usually use this substrate and manufacture integrated circuit. इसमें तो मैंने एक approximation is a scientific instrument used to test and measure very small electronic devices and semiconductor components. It helps research check how tiny circuits, chips, or sensors work before they are fully manufactured or packaged. The system has a very fine metal probe that touches specific points on a small sample or wafer. These probes are connected to measuring instrument like multimeter, oscilloscope, or analyzer to record electrical signals. The entire is placed on a table. The entire setup is placed on a stable platform. Okay. So, practical implementation is semiconductor device testing, IDCB and transistor characterization, wafer level measurement before packaging or design. Material and thin film analysis for resistivity and conductivity studies. The main purpose of semiconductor device testing
जीवेश सर थोड़ा लुकिंग का रिक्वेस्ट आ रहा है माइंड से वो थोड़ा एक्सेप्ट कर दीजिए ओके आई विल डू हाँ इसके नाम yes yeah please continue
okay so basically processor में आप देखिए तो semiconductor device testing के पर्पस में यूज होता है semiconductor device testing IDCB and transistor characterization इसमें wafer level measurement और before packaging को pricing के पर्पस में उसको resistivity और conductance और माइक्रो लेवल वोल्टेज को हम चेक कर सकते हैं और ये प्रोसेस एजुकेशन रिसर्च और R&D यूज के लिए काफी मतलब ज्यादा यूजफुल रहता है इसके अंदर आप ACD फेलर्स और उसका एनालिसिस कर सकते हैं क्वालिटी को कंट्रोल करके चेक कर सकते हो सेमीकंडक्टर डिवाइस में जैसे हम IV कैरेक्टरिस्टिक्स निकाल सकते हैं ट्रांजिस्टर की कैरेक्टरिस्टिक्स को हम निकाल सकते हैं और इंसर्ट डिवाइस में डिजाइन स्पेसिफिक इंक्लूड सर्किट स्पेशली काफी ज्यादा डिजाइन चलता है ये आपको 10 माइक्रोन से 10 माइक्रोन तक की पोजिशनर्स में मिल जाते हैं जिससे आप काफी ज्यादा प्रिसाइज और माइक्रोमीटर के अंदर आप प्रोब्स को टेस्टिंग कर सकते हो जिस तरीके से सेमीकंडक्टर में सेमीकंडक्टर वेफर प्रोब जो वेफर रहती है उसके अंदर ट्रांजिस्टर के कॉम्बिनेशन रहते हैं और ट्रांजिस्टर के कॉम्बिनेशंस के अंदर आप जो भी अब उसकी वोल्टेज लेवल को मेजरमेंट करना है तो आप उसके लिए प्रोसेसर का यूज करके इतना आप इमेज शेयर कर दो तो आप इस तरीके से मतलब ट्रांजिस्टर्स की कॉम्बिनेशंस रहती है जहां पर आपको आपकी प्रोब को सेट करके वोल्टेज और उसके आईडी कैरेक्टरिस्टिक को मेजर कर सकते हैं तो इस तरह कर सकते हैं और प्रोसेसर की काफी सारे टाइप्स आपको अवेलेबल हो सकते हैं काफी डिफरेंट टाइप्स के आपको प्रोसेसर आपको जैसे टेम्परेचर कंट्रोलर प्रोसेसर जिसमें आप वेरियस टेम्परेचर को कंट्रोल कर सकते हैं वोल्टेज रेजिस्टेंस और कैपेसिटेंस को मेजरमेंट कर सकते हैं। इसमें से टेम्परेचर कंट्रोलर प्रोसेसर के अंदर हमारे पास में जो एक बेसिकली एक चक होता है, इसके अंदर हम डिफरेंट टाइप का रूम टेम्परेचर से 200 डिग्री सेल्सियस तक की एक टेम्परेचर को सेट कर सकते हैं, जिसमें हम वेपर को वैक्यूम करके उसको डिफरेंट टेम्परेचर में करंट और वोल्टेज और रेजिस्टेंस को मेजरमेंट कर सकते हैं, जिससे हम उसकी एसी की टेम्परेचर की टेस्टिंग कर सकते हैं कि कौन सी टेम्परेचर को उसके अंदर स्टोर होगा। एंड ये वैक्यूम चेंबर विद प्रोब स्टेशन, इसमें सिर्फ वैक्यूम एक प्रोब स्टेशन को हम वैक्यूम चेंबर में मतलब रख सकते हैं और वैक्यूम से हम उसको एक प्रेशर जनरेट करते हैं, जिससे प्रेशर जनरेट करके उसको
Yeah, hello.
Yeah. Viewers,
Yeah, you are audible. Continue.
okay. So, sir, first of all, I would like to, as my colleague Tushar is going on the presentation, but due to some reasons, now I am Mubin Agarshik. I will continue this presentation for the purpose of demonstration, for demonstrating this presentation. So, sir, first of all, if we talk about the probe station, so we want to tell you that we can able to make every type of probe station in terms of customization. If any customer who has required any specific kind of probe station, we can make it for we can make it for them. So, sir, first of all, the thing is the probe station has some major parts, such as in the presentation in the screen, you can see that the micro positioner. This is the blue color things. The blue color devices are called micro positioners. The circular object you are seeing in the image is the chuck, and other things are only just for mechanical stability and some kind of vacuum generations. So, sir, here we can make modification in all manners, such as if you want to make some kind of micro positioner, that you want to make some specific arrangement for your purpose of testing, such as you have some material and you want to clip it, or if you want to make some kind of changes according to your data. So we can make a micro positioner. We can make change our micro positioners as per user request. Also, as the Mr. Tushar has told you about some kind of probe station. So, sir, we have make already different type of probe stations. So here you can see our temperature controlled probe station, where we can change the temperature of chuck. Here we can change the temperature of chuck up to 200 degrees Celsius right now, but we are able to work with around 400 degrees Celsius. So from the room temperature to we can go up to 400. In the slide you can see 200, but we can go up to 400 degrees Celsius with the chuck. So if you have a material that you want to test on high temperature regions, so this is the reliable for the purpose. But the same thing. Hello, I'm audible, sir? Hello. So the same thing. If we have to require that we have to test our material on
Yes, you are perfectly audible. Please continue.
yeah. So if we have to if our requirement is based on low temperature, such as if we want to test our materials on negative temperature, so we have also some solutions. Here you can see that the vacuum chamber apart from probe station, we also made vacuum chamber. Actually, we have delivered some. Here is a case where we have delivered a vacuum chamber with probe station. Here you can see the image of that product. That was delivered in IISCR Bhopal, where we have delivered a vacuum chamber of around 450 by 450 mm. And in between the in this chamber, we have put the probe station. What user do that? User will set his probe, his sample size in the vacuum chamber. He will probe the micro positioner according to wafer. Then after completing the wafer probe station connections, he will close this chamber and make a vacuum. After making vacuum, they will insert some kind of gases to see the impact of changing environment on the material. So this kind of this kind of experiments and research can only be done by the vacuum chamber based probe station. So we have a separate segment where we can develop a vacuum chamber and probe station. If anybody want a vacuum chamber for their purpose, we can also we can also make these things. So as we talk about the negative temperatures, so sir, we are working in cryogenic probe stations. So these are the cryogenic probe station. Each of the probe station have some specific cases according to user needs. So you can see that the shapes and photos and changes. Photos are very different. So in that case, we have a negative temperature. I can say that the probe station can go up to -100 degrees Celsius by using this setup, where we will provide a vacuum environment. Apart from this, we have a there is a shielded probe station. This is another case which we have delivered in IITs. In this probe station, we had provide us totally EMI proof covered to user with probe station, where he can do all his experiment on this overall enclosure. And so these are some customized products and customized domains where we can develop the probe stations and material science based equipments according to user needs. Apart from this, if we are going specifically on probe station, we can modify it in different type of domains. So here you can see that the stable platen mount. So the platen is a very important part of the probe station. So we can provide up to 10 micrometers of planarity in surface area of platens. Here you can see that this is the U-shaped platens. We can do this in as per user needs. So the surface planarity of the platen is around 10 micrometer or less than 10 micrometer, so that we can put our micro positioner on their platens. And so sir, here in this slide you can also see that there is a XY stage. This is have you seen my mouse?
Yes, sir.
So this is our XY stage. So according to user need, we can change solution of this particular stage. So from 100 micrometer to 10 micrometer, we can provide different type of cases where you can get resolution of x and y direction in 10 micrometers. You can get theta. Theta, that means you can change the angle of chuck according to your needs. So we can go up to 360 degree with the 0.5 degree of resolution, 0.1 degree of resolution as per needs. Here you can see that there is a vacuum pipings are here and individual switches are provided at the side of the base. So according to sample size and according to sample sizes and wafer sizes, we can change our configuration of vacuum switch from here, and we will get some the vacuum output at the surface of chuck. This is our circular shaft. So these parts, as I described here, discussed here, this can also be customizable. So, sir, if you are working in some kind of material science domain or in any kind of sample testing domain, where you want to do any kind of customization, we are here to provide you the proper facility with our entire factory. We have a manufacturing for mechanical items. We have a complete mechanical setup for doing this. Here you see all the equipments here are made in India in our in-house production facility. So we can do any kind of changes according to your need if you require. So first is we have our standard products. Another part is we have our you can customize it as per your need. Every part is customized can be customizable in this overall setup. So third is now the next thing is support. So sir, if you do any kind of changes in your home station in kind of with respect to customization, here we are here we are providing complete full guidance and support after delivery and previous delivery. We had to approve the design and then we will work according to user needs. So don't worry about that. After delivery, what will the response of the suppliers? We will help or not. So we are here for completely. We are here to provide you support 24 hours. If you purchase any kind of customizable thing, then you will not find too much data on our website or internet, but we will here for providing online help. If required, our engineers comes to the sites and they will provide complete installation process and so on. Here, one thing is I would like to describe you that our XY stage is completely backlash free. You will not find any backlash in our XY stage. Even if you are purchasing our microversions, these are also completely backlash free. Sir, have you doubt any query in this particular slide, sir? If you have any question, then you can ask me.
Anyone have any question? No, please continue.
Yes, why not?
Sir, here, actually, this is not from the mechanical side. If you are from electrical or electronics domain, here you can see that we have different type of tip fixtures. Let's suppose if we are if you are talking about the micro positioners, so you can see that this micro positioners have some stands such like for tip holding. This is called tip holders. Here you can see that this is the tip holder where we can mount our tip. So how we will mount it just by using this screw. So after the head attachment, you will find this kind of total mechanical assembly over there, where you can tip and probe your wafer. So here, according to user needs, here I show you in the last. This is our tip.
The question is,
Yes.
have you checked the cryogenic operators?
Yes. If as I showed you the cryogenic probe station, this was this. So in this the tips are here, and you have to use some forceps or kind of such kind of holding things. You have to put your material over onto the this white circle. Then you have to put your tips via forceps, and you have to probe that material. Here you can see that X direction movement. Here, in the you can see that this is a rail-based movement. Here is a rail. Of course, you can vary the distance if you have to require, and from that point, the angle of tip can be changed. From this point, the tip, so you can get complete XYZ movement. But these are manual you have to press, but you have to press this manually. So after pressing on the after placing your material, or I can say wafer onto this chuck, you have to probe this, and then there is another cover comes up with this probe station. You have to mount on the top. They will provide you with completely airtight, and they will provide you completely airtight environment. From here we can provide vacuum, and these are the input-output ports, where 1, 2, 3, and 4 for these 4 stations, for 4 blocks. Here we will get the output, and if user want that if I want to work with some kind of negative temperature, so we will provide liquid nitrogen in this chamber by using this port. If anybody wants that I want to work with the negative and positive work temperature, then we will put up a small heater inside of this rectangular assembly. So what is that? Yeah, inside this square assembly, because this is a kind of metal block. If we put up a heater inside, then we can change the temperature in positive direction. As if you don't want to work in positive direction, then we can provide liquid nitrogen from inside from this point. So we can get a vacuum. Obviously, we will get a vacuum environment with negative and positive temperature very facility. So here we are working for this probe station right now, and we are working for minus 196 degree to 400 degree Celsius. This is our minus 196 to 400 degree Celsius. 400, yeah, minus 196 degree Celsius to plus 400 degree Celsius. This is our range in that we are working. So if user asks if you have a requirement in this temperature domain, then we will help you for according to your needs.
Sure.
So here in this slide I was describing our multiple projects. So in last around 2021 we had done a project where user want to make some tip fixture for compiling this project. So here we will make a tip fixture where you can see that we are providing 3 tip, 1 tip, 2 tips to up to 12 tips. So by using a single micro positioner, you can just put up 12 tip of specific direction on your wafer, and you will get the data. So you just do not need to use a 12 or 13 micro positioner. Instead of that, we will use a single micro positioner where this tip fixture will be mounted on that, and you will get the data from that tip fixture. Here, these are our vacuum based chuck, in which we provide drills in that circles that will create a vacuum, as I earlier described before that. This is our vacuum drills. One thing more, according to user needs, we have developed 2 types of sections. Let's suppose this is the precision positioners, where you will get the precise movement from upper side of sections, and you will get force, that means fast movement from this section. So you will get, and this is our highly there is a powerful magnet that will be work according to user need. There is a button you can switch it for whenever you move the particular button, the magnet in the bottom side magnet will be activated and it will completely stick on our platen, and then after that we can move our micropositioner as per our needs in course in 5 directions. So this is the another product that we will make according to user needs. Apart from the precision measurement, we had to provide our some kind of accessories such like we had to provide low noise vacuum pumps with that will create very low noise and provide you a very better output. This is our one of the vacuum pump that we had used in our micropositioner. This is a 7 LPM output of vacuum pump. Here is another setup that will deliver earlier in some NITs. Apart from that, as I described, we had to do customization in micropositioners. So we have a standard micropositioner from 100 micron to 1 micron of resolution. If you want to if you want 1 micron resolution, we can provide you. If you want 100 micron resolution, we can provide you. In between the range, we will provide you all kind of customization. So many times customer said that we have to change that section and that will be used according to our needs. So we will change that other things and provide the customizable solutions to users. Sir, are you work from material science or other departments?
Yes, material science.
Yes. Okay. So, apart from PV station, we have also selling furnace for the purpose of material testing, where we will get the dielectrics constant and resistivity of the material. So, if you require in terms of furnace, then we will provide you completely furnace setup with sample holders, where you will get the temperature of room temperature to 1000 degrees Celsius, and we will provide you a standalone software where you will get at least 24 to 25 type of parameters of any material, and there is a facility to make the graph between the different type of frequencies that you will apply on material with respect to temperature, with respect to resistivity, with respect to dielectric constant. All these things you will get on a single window. So and also we are we show that we are also working in a low temperature. So we have also travel states where you can put up your materials and you can test it up to minus 180 to minus 190 degrees Celsius. And the same things, the same software will come along with that setups. So if you require, then you can ask for NMAX. We can provide them the catalogs and all the details. So if anybody wants to change the probe station patterns, so we will make the patterns according to that. In case of I already discussed for chuck XY stages and different type of chucks. If in case of chuck, many of the users require different type of plating such as nickel plating, golden plating, silver plating, platinum plating. So we will provide the different type of plating on the surface of the chuck according to needs. Apart from this, we have provided two types of probe stations. Here you will see that there is a studio zoom camera, which is heavy advanced. This is highly advanced system that is used to analyze the paper data here for visualizing purpose. But if you have any low budget, then we will we may change we have changed into a normal USB camera where you will there you will get a simple USB camera on the home station, and you can do the same work with that. If you have any proactive requirements that already I have discussed, we had designed different type of proactive folders, and if you required around 1 micron of tip, 2 micron of tip to 10 micron, 100 micron of tip, we will provide you on the as soon as possible or best ways. So, sir, the main objective of our presentation is that customization and flexibility. So, because in case of every research, every unique research, we have to do some customization according to our needs to make faster innovations. So, here, if you have any kind of customization, you can ask us. You can ask us to LMAC, and if you want to purchase anything, then you can also contact to LMAC, which is our authorized dealer for the probe stations and the material science department, material science equipments. So, sir, if you have any doubts, then you can ask me. I will clear you. This is our basic presentation. I hope you understand well, and thank you for giving us time. So, sir, if you have any queries, then you can ask.
Yes, anyone have any question? No. So basically, we saw the different kind of station and what kind of things can be supplied from your side. So only one query I have that temperature range. Are you working in the range of 4 Kelvin for room station? Means
Sir, actually, if you want to work in the temperature range, then we can go up to -196 to 400 degrees Celsius. That we are working on that.
-296.
-296.
Sir,
yeah. So, sir, actually, here we can, if I am frankly saying, we can achieve -195 practically here. We are working on below from the stage.
basically, you are working on the cryogenic process. You are using natural gas,
Yes, sir. We are using nitrogen basically, but we are working. We are continuously because we have a one setup, so we are continuously working on that things. So these are the things you are talking about helium based cooling. So these is in our process. So when we have completed, we can.
Okay, fine. So thank you. I think this was the query from our side. So thank you for giving us valuable time and giving the presentation. So it's thanks to the speaker and thank you. Thank you. Thank you. Yeah, so I was discussing about again finish this. So basically I was saying that so many parameters you have to measure in characterization. One thing you will learn how to find the contact resistance, one thing how to find the seat resistivity and device perspective. Another thing you have to find out the threshold voltage also. If you make it transistor, you have to find out the threshold voltage. There are two methods people are following using the find out the threshold method. One is using IDVG. IDVG you can characterize. IDVG you can change the gate to source voltage, you can find out the current, and then you can characterize to look at the IDVG, right? And then what you can do, threshold voltage you will use to achieve where the significance of current you can get it, right? So one method is using IDVG. People are getting this kind of characteristics, and then people use to say find out the cutoff, how much cutoff this is, and this will be the threshold voltage. They can estimate. Okay, this will be the threshold voltage, or better, you plot this in the log scale. If you plot in the whenever you will get the saturation in the log scale, you can find out threshold voltage here. So best way to find plot voltage in the log scale. Right? So this is using the IDV, but best accuracy with this one voltage will come if you do something on a CV value. Okay. Capacitance versus voltage. Some advances you mentioned. These features also you can find out. You can make any capacitor and you can do the CV with capacitance versus voltage. If you don't have this feature in your CV, then it's fine. You can do the IDV characteristics. If you're using the log scale or linear scale, you can find out that this one voltage. Not a problem. It's fine. Totally fine. CV measurement. What is the CV measurement? Basically, let's say probably the MOS capacity. Metal oxide semiconductor. Metal, let's say this is metal, it's an oxide and this is semiconductor. Standard MOS capacity. Metal, oxide and semiconductor. So if you have to find out the capacitance, whenever you have to find out the capacitance, you can apply voltage between these 2 points and you can find out the two conversion tool will transfer the SMU and for SMU, this SMU has the capacitor measurement unit that will give you the capacitance on corresponding voltage and corresponding frequency also, right? So it will give you the capacitance value. So the comparison is some capital ones that we are not covering this here, but I will just tell you that how to find out the value. So basically, if you talk about the capacitance of this, you know the standard capacitance CH, Ka, epsilon by D, right? So if you want to talk about the capacitance of any MOS structure, for example, so here if you want to talk about, let's say this is a P-type semiconductor, it's completely doped now. P-type semiconductor completely doped. In this case, you have carrier from here to here, right? You have carrier from here to here. You have carrier from here to here because this is metal. So only capacity part will be your oxide. So if you take total capacitance here, A epsilon naught by D, Ka epsilon naught by D is A will be area of this layer, epsilon naught is known, D each whatever the oxide will thickness is there, that will K will be the dielectric constant of the oxide. So this will give you this. But what happens if you apply increasing the positive voltage? Let's say if you are in deep, if you apply increasing the voltage across, let's say positive voltage here. Moment you will start applying positive voltage here, what will? So whatever hole is there, that will be start. This system will start repelling whatever hole is here. So hole will start coming because you are applying positive voltage, it will repel all the hole. So hole will start coming this direction, right? So wherever this plate is here, the depletion layer will start generating here. Depletion layer, right? So the moment depletion layer will start generating here, what will happen? You have additional capacitance will be the depletion capacitance will start coming into picture. So then in that case your another capacitance will be CD, that will be your K, A epsilon naught by D, where D will be your depletion rate, how much your depletion rate for that particular time of the voltage, and area epsilon naught, and this time this K will be your dielectric constant of that depletion region. Fine. So two capacitors will come into picture. In short, what will happen? So you are putting two capacitors into parallel, right? Sorry, series. So your overall capacitance will decrease in that case. Ultimately, you can see that your D is increasing, your overall capacitance will decrease in that case. So what will happen if you take a standard CV? So on deep negative, your capacitance will be almost constant, and then at certain voltage, at certain positive voltage, it will start decreasing, right? If you continue voltage, this process will continue until unless inversion will start. But parallelly, what will happen? This positive voltage will start pulling electrons also towards the plate, right? So after complete depletion, there will be a point where the complete depletion will happen, and then electrons start coming towards the plate. So at the time of complete depletion, what will happen? Your capacitance will have minimum value, because at that time you have complete depletion. Let's say this one will come to this point. So this will give you completely this. And then again, suddenly what will happen? The all electron will start coming, and then again this will be filled by electron, which will be in the inversion rate. Inversion. So suddenly what will happen? You will see sharp increment in the, and then it will you get constant. So sharp increment will happen into the inversion. Suddenly it will come. So what is threshold voltage? Threshold voltage you will where you will get the inverting channel, and its carrier concentration should be similar to the previous concentration. So the voltage by your channel is getting completely inverted. So this is your voltage where you are getting completely inversion into your channel. So by doing CV characteristics, this can be your threshold voltage. Fine. So either you can find out this way, or you can find out this way. I suggested initial level, don't go for the CV measurement. Just you can do the IV characteristics, IDVG characteristics, and you can find out threshold voltage. So now threshold voltage is known for you. Fine. Then what other things you have to find out? Try to find out all the unknown things. Second thing, you have to find out mobility, which is known as field defect mobility. This mobility device give you in the presence of total field, right? So it will be different from the intrinsic mobility or intrinsic carrier density. So you have to find out the field defect mobility. What you can find out just to differentiate this equation with Vg, di by dvg, di by dvgs. What will be this? 1 by 2 mu Cx W by L into 2 into VGS minus VGS, right? Fine. So sometimes what people use to write, they use to write VGS minus VGS VO OB, V over drag. So this is equally just VGS, so no problem. So main thing is that since you have ID versus VG, you can plot DI versus delta I versus delta VG also. Just extensive you have to find out delta in both cases. You can plot delta I versus delta VG. So if you plot delta I divided by delta VGS versus VGS, you can plot it, right? It will give you a linear equation. It's linear equation, right? If you plot with shifting also, with over drag also, then whole slope should give you this mu Cx and W by L, right? If you plot delta I with delta VGS with VGS, then it should be linear equation and slope should give you mu Cx W by L. W by L is known. Cx you can find out oxide capacitance using the CV measurement. Because standard capacitor, or if you know the dielectric constant of the oxide, then you can calculate Cx. So you can find out the mobility of your device. So this way you can find out the field defect mobility. Right? Sometimes what happens that understood? And then if you have mobility and GM and other things also you can calculate. So that's why you are seeing. So basically from the standard IP characteristics, you can find out the source voltage, you can find out mobility, you can find out all contact resistance, all the things you can find out by just started doing the characterizing method and by knowing how to extract the different kind of parameters. Okay. Then sometimes what you have to do, CV measurement will help you to find out defect, traps, and other things also. Because since if you can understand the capacitance, you know the capacitance C equal to Ka epsilon naught by D, right? So if you have your oxide thickness, whatever oxide gate oxide you have, you have certain trap states, certain ions and other things. Then what will happen? Your K will change. Dielectric constant of oxide will change. So by just measuring the CV measurement, by doing the CV measurement, you can find out the quality of dielectric constant of your oxide. And if you find extract the dielectric constant of the oxide, then you can figure out if there is any impurity in the oxide or not. Because if there is any impurity, then it will not match with your ideal value. Fine. If you go for certain advanced method, then you can find out what's called trap charge, ion, and other thing also. Because if you have any oxide, let's say there are some electron get trapped into this. If there are certain electron or certain charge will get trapped into this, it will impact your overall capacitance because you are assuming that your capacitance is this, but effectively it's not getting this because you have certain mobile charge inside that will disturb your capacitance. So by measuring the capacitance, you can find out how much impurity inside this region. So using a standard CV method, there are certain advanced methods using that you can find out the phase charge and other things also, which we will not discuss in detail here because that will be advanced methods. So basic thing that using a standard IV only, we can find out load voltage, mobility, contact resistance, something known as dynamic resistance. Dynamic resistance means how resistance will change with the voltage. That we can find out by IDVD. If you have ID versus VD equation, you can calculate, then you can find out that also. You can explore about that by yourself. So, what sort of things we can find out? So, due to shortage of time, we can stop it here only. If you have any question, then you can ask. Any question? So, after this threshold voltage, of course, you can increase. After this one voltage, if you increase, then only it will give you characteristic IDVG. Then it will give you characteristic. But if you go for very high, then of course it will give you damage your device. And there are soft damage and hard damage, catastrophic failure. If damage in terms of the impact ammunition or other thing, that can get recovered. But damage can be in the bond breakdown also. If you go for increase electric failure very hard, then that will give you that catastrophic failure also. So of course, don't increase voltage very high. So there is separate testing. This is reliability testing of the device. Separate testing. You have to find out the breakdown field of your device. Where background is happening, background can happen in contact, background can happen in channel, or background can happen in any other thing also. That all depends on the how much field you apply and how effectively operated it is. This is separate field of reliability testing. So that
Depending on operating
and depending on the device is not depending on operating code. Operating code is important if you are doing silicon art level. Operating this a catastrophic failure will depend on the material. At what millimeters of bone will break. So if you will apply very high field, if that particular field density bone will break, then it will break. Always you have to apply field, so don't see voltage. Always when you are applying any device, always find out field. See the standard V divided by L and see whether this field will be lesser than the bond breaking field of that particular material. Always be sure about it. When people say okay, 5 volt, they used to apply in 1 micrometer distance also or 1 nanometer distance also to break your device. Because usually for silicon, I think you can figure out some megavolt per centimeter or something in the breakdown field, 100, 3000 something. So in this range, so always you have your field has to be lesser than its bond breaking field. Otherwise, the ground will break and your device will part. Any other question? Any other question? Okay, if no more question, then we can stop this session here. And this will be the final session of this was the final session of this camp program, final lecture session. We'll have one more tutorial session. It will be the next half. So what I will request you all to please have lunch. And after lunch, you can assemble in the lab. What you've seen the lab, right? Come on, only where first will demonstrate you about the probe station, SMU, how to do the probing, and how to do the electrical preference. After that, we'll come meet here. We'll have an evaluation and the preliminary session. So once you finish there, please come as soon as